All right, boys and girls, we're going to have to do 2 5-minute lessons for this section. There's just a lot to unpack, and it's called the fundamental theorem of calculus. And so we should expect this is a pretty big section. We will actually be doing integrals now, definite integrals, okay? And today, this first 5-minute lesson, we're going to do these first 3 bullets. So we're going to go over the fundamental theorem of calculus. We'll talk about the mean value theorem for integrals, and we'll show how to find the average value of a function. These 2 things are directly related, okay? So I would watch this video. It's just 1 minute, and it's going to tell you about the fact that you are now done both branches of calculus, differential calculus and integral calculus. And what the fundamental theorem of calculus says is that these 2 functions are inverses, okay? I would read through this pretty closely because it's kind of neat, but it basically is explaining it like, think about derivatives. We were finding a limit of delta y over delta x, whereas integrals, we're finding the limit of the products of delta y over times delta x. So you got kind of like division and multiplication. And this just kind of gives you a hint of why these things are inverses. Here you're seeing that a secant line became a tangent line in a very similar way that an estimation of an area became an actual area. And then this section, again, pause the video if you want. I have learned this many times, and I have reviewed this for like an hour before making this video. So feel free to pause the video, or more importantly, read through your book slowly, okay? This is showing you that anti-differentiation and definite integration use the same symbol, this sum sign, okay? But they are not exactly the same thing. Remember, with anti-differentiation, you have to add a constant plus c. That's not going to be necessary with definite integration, and we'll explain that later. Okay, here's the fundamental theorem of calculus. It says that, hold on, this isn't going to work. It says that the integral of a function is equal to its parent function. That's the antiderivative. We'll go into that in a second. That's the same function. So all you do is you put the top number in first and subtract the bottom number, and that gives you the area under the curve. That gives you the definite integral. Okay, if you want to go through the proof, if this interests you, come see me and we'll go through it slowly together. We're going to skip through it for the video. Here's some guidelines for using the fundamental theorem of calculus. Provided you can find an antiderivative, then you have a way to evaluate a definite integral. So they're kind of indicating you won't always be able to find the antiderivative. We can talk about that if you want. Okay, here's an example. Look, kind of a simple example. X cubed. So what's the antiderivative of x cubed? Well, we got to add a power and then divide by it. So if you took the derivative of this, it would give you that. That's what an antiderivative is, okay? So notice x cubed went to x to the 4th over 4. And now what we're going to do is we're going to plug in the 3. And then we're going to plug in the 1, and we're going to subtract them. Okay, so what this tells you is that the area under a curve x cubed from 1 to 3 has an area of 20 square units. Okay, down here we start to see why it's not critical to add the c value, because the c value, if you added it, would be subtracted out. Plus c minus. This indicates why you do not need the c value, okay? This just shows you a couple other ways to write parent functions. Let's go ahead and do part A here, okay? The integral from 1 to 2 of x squared minus 3 with respect to x. Okay, so we're integrating this with respect to x, which means we're finding dx is the base. We'll talk about that, I guess. So what's the integral of x squared? Well, that's x cubed over 3. What function gives you a derivative of 3? Well, that's 3x to the first over 1. And we are evaluating that from 1 to 2. So how do we do that? We put in a 2. That's 2 cubed is 8. 2 times 3 is 6. And then we put in a 1. 1 cubed is 1. 1 times 3. Okay? So you end up getting negative 2/3. Yes, negative. This means that this function is below the axis, at least partially. And again, you'll see examples of that. We kind of addressed that a little bit in yesterday's 5-minute lesson. Notice some more examples. How do we do 3 radical x? Well, first we factor out the 3 and we turn the radical x into x to the 1/2, add 1 and divide by that, and then plug in the 4, plug in the 1, and subtract, and you get 14. Again, this is a 5-minute lesson. You guys might need to slow down on these. Okay, here's a definite integral involving an absolute value. This is kind of a particular. I think we should just graph these. And look, you're going to split up absolute values. We talked about that last time. See how we do it. See how we do it. Okay, here's another example. You should read through the examples, but we got to get on to the mean value theorem, okay? The mean value theorem for integrals just says if we have a function that's most likely a curve, and we have this area under this function. Oh my gosh, how frustrating is this? Whoa! Whoa! All right, well, you get the idea. The area under the curve could be not approximated, but completely matched by some rectangle with the exact same area and the exact same base. And if you did this height right here, that is your average height, the average density of this function, okay? So the mean value theorem for integrals just says there is a rectangle that gives you the same area as you have under the curve. And then what that leads us to, whoops. Let's see. It leads us to be able to find the average value of a function over its, so here we go. So let's think about this. Think about this like snowfall, okay? So let's say it started snowing at 1 o'clock and it ended snowing at 3 o'clock. And this function was not how much snow was on the ground, but how much snow per instant, like snow per hour. The average snow per hour rate is changing over time, okay? So if we added up, if on this we had inches per hour, oh no, this is hours, excuse me. If down here we had hours, why won't this work right? Hours. And up here we had inches per hour. And we're finding the area under that. If you do inches per hour times hour, you get inches, this thing. You get inches, okay? So if we can find the average value, we can find like the average amount of snowfall per hour. We can kind of like estimate it. This is how this is actually done, okay? So this is a proof. We're going to skip by the proof and we're going to look at an example. I'm not going to go through this by pen. I'm just going to walk you through it because this is about the end of the length of the video I wanted. So look, here's a function. The integral is from 1 to 4. So it's snowing at this rate from 1 o'clock to 4 o'clock. Okay. What was the average snow rate? All right, well, you could do 1 over 4 minus 1, so 1/3. And then you got to take the integral of this. So this is 3x cubed over 3. That's x cubed. 2x squared over 2. That's x squared. We have to evaluate it from 1 to 4. You put the 4 in first. You put the 1 in second. And you get 48/3, which is 16. So on average, this function's height is 16. Look, the function goes from here to here. This is all of the area under the curve. This is the rectangle that would equal that area, and the average value of this over that is 16 inches per hour if we're measuring snow. Uh-oh, no, we don't want to do this yet. I just wanted to show you the speed of sound. This is pretty sweet. I had no idea about this. All right, so look, the speed of sound changes based on your altitude. I had no idea, and look how crazy the graph is. So this is sea level. The speed of sound is 342 meters per second. And then once we get to 10 kilometers above Earth, the speed of sound drops significantly, 295, and it stays there for a while. And then for some reason that I'll never be able to explain to you, it goes up again, and then it drops sharply again. So then what is the speed of sound? Well, it depends on where you're at, but what about the average speed of sound? Well, we're going to have to calculate the integral here, the integral here, the integral here, the integral here, and then the integral here. We're going to have to add them all up, and then we're going to have to divide by 80, or multiply by 1/80th. So look, that's what we're doing. That's what we're doing. We're just adding up all these little integrals. Okay, 0 to 11, 11 to 22, 22 to 32, 32 to 50, 50 to 80. We're getting all these different areas. We're adding them. This is the total sum underneath. Doesn't mean a whole lot to us, but then when we divide it by 80, the average speed of sound is 308 meters per second. Pretty cool. You guys are so smart. Boom!